In this example, we're asked to find an infinite sum contained in this triangle right here, this finite little triangle. And what we're asked to do is find the sum, which is, so I'll call it S, and it's going to be equal to CD plus DE plus EF plus FG plus ... and so on. So what we're doing is we're finding all of these pink lines here, the perpendiculars, this plus this plus this plus this plus this plus this, and so on, all the way off to infinity. Now, you may notice we don't have any numbers here. It's all letters. And so we're also told to find this sum in terms of b and theta. So I'll put in terms of b and theta. So they want us to only use these two things in our answer, aside from regular numbers like 1, pi, etc. Now, this little b right here, you could have called it AC, but they just decided to label it b. So that's this whole length right here. I think the reason they did that is that it's not part of the sum. Notice this length right here. You only start here and go from there. And theta is this angle right up here. So first things first, let's look at CD. Let's figure out what this first term is and see where we can go from there. Let's see if we can figure out what each one of these is and if there's going to be a pattern. So if I want my answer to be in terms of theta and one of the sides of this triangle, that brings to mind trigonometry. So that brings to mind like sine, cosine, tangent. And so I'm going to look at this triangle and see which trig identity would make sense. So if I look here at theta, if I do cosine, that would be adjacent, which would be b, over hypotenuse, which, oh, actually no, because if you look at this, this is where the right angle is, right there. So you have to be very careful about that. It can get confusing when it's upside down and flipped around like this. Actually, if I did cosine of theta, that would be this side right here, dA. And then the hypotenuse is little b. So this would be dA over little b. And if you look at this, that really wouldn't make sense for me to do because I don't have a dA anywhere here. Whereas if I did sine, sine would be opposite, so that would be CD over hypotenuse, which is little b. And I do want to figure out what CD is. So let's do that just over here. Sine of theta is equal to CD over b, little b. All right, well, we're trying to figure out what CD is. So I'm going to take this and multiply both sides by b. And that gives me that the side CD is equal to b sine theta, which is pretty cool. So I'm going to put that right here. B sine theta is my first term. And then we need to figure out DE, EF, and FG. And hopefully by the second or third one, there'll be a pattern we can see. So now, if we look at what's going on here, I need to figure out what DE is, this side right here. And if I want to keep using sines and cosines, I need to figure out the angles inside this triangle here. Well, the way that's most obvious to me to do this is to realize, well, the sum of all the angles of a triangle is 180. So this is 90 degrees right here, this little box shape. And so I'm going to label this side right here, or this angle down here. I'm going to call it alpha. And alpha is going to be equal to 90 minus theta, 90 degrees minus theta. And notice that makes sense because if there's 90 degrees here, then between these two guys, there's only 90 to spare. So if I add them up, I should get 90. Notice alpha plus theta, the thetas would cross out and you'd have 90 degrees. So if this is alpha, which is 90 minus theta, and if you look at this whole angle right here, like this whole side, that's also a right angle of 90 degrees because that's the base of this larger triangle. So this has to add up to 90 degrees, which means that this angle in here must also be theta. And so if you look at this and you go through the steps very carefully, you can see that you'll have theta, alpha, theta, alpha, theta, alpha, and so on. And you can keep filling that out. So for now, I'm just going to focus on this triangle. I'm trying to figure out what DE is, and I have theta right here. Once again, sine of theta would be DE, opposite, over the hypotenuse, but now the hypotenuse of this triangle is actually CD, or DC. The order doesn't matter, but I'm going to be consistent with what we've got here. So for this, if I do sine of theta, let me cut those, doing separate things. So sine of theta is going to be opposite, which is DE, over hypotenuse, which is CD. Well, what are we trying to find right now? We're trying to find DE. So multiply both sides by CD, and we have CD sine of theta is equal to DE. Now here's what's really cool. I could just go ahead and put here, okay, cool, so DE is CD sine of theta. But remember, they want the answer just in terms of B and theta. So now my question is, well, what is CD? It's B sine theta. So actually, if DE is CD sine and CD is B sine, we're going to have B sine times sine. So B sine sine, that's going to be B sine squared theta. And so if you notice, we've got B sine squared. I'm going to do one more side, but you can probably see the pattern now. I'm going to go quicker with this one because it's going to be the same kind of logic we've been doing. If I look up here, now theta's on top again. Sine of theta is going to be EF, because that's opposite. EF over DE. Opposite, EF over hypotenuse, DE. Once again, multiply both sides by DE, and we get that EF equals DE times sine. And what is DE? DE is B sine squared. So B sine squared times sine is going to be B sine cubed. And so this one right here, this FG, this is going to be B sine to the fourth, and so on. All right. So we found an expression for this. The sum is equal to B sine plus B sine squared plus B sine cubed plus B sine to the fourth, and so on. However, they're asking us to find the sum, because if you just know series in general, maybe this doesn't converge. Maybe this just diverges and explodes. So we need to actually find a closed form. We need to find a formula just with b's and sines that gives us one value given a b and a sine, a b and a theta. So, well, here's where we need to get a little bit clever. So if you look at this, it doesn't immediately look like any sort of form. I'm going to put this in sigma notation. So this is going to be equal to the sum, and I'm going to start in at 1, and I'm going to let it go to infinity. And we've got b. Notice the b doesn't change, just b, 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 and so on. So there's no n attached to the b here. Sine to the, well, it's to the first power, and then the second, the third, the fourth. This is the thing that's changing. So b sine to the n of theta. So this sort of kind of looks like a geometric series, because a geometric series is the sum n equals 1 to infinity, a, and it would usually be r to the n minus 1 if it's in like the proper form. And so as long as r, the absolute value of r, is less than 1, that is, it's a number between -1 and 1, then this series will converge. And the sum of a geometric series, again, as long as this is less than 1, sum of a geometric series is going to be the first term, which I'll call a sub 1, over 1 minus r. So this is what we're going to use right here. However, again, r has to be less than 1. And if you think about it, well, wait a minute. Sine isn't always less than 1. What if I put in 90 degrees here? Sine of 90 degrees would be 1. And this doesn't say less than or equal to. This says less than. Well, here is where you have to get a little bit clever, or maybe not clever, but observant. And people tend to miss details like this because we've been doing all this work up to here, setting up the sum, and now we have this, and it's like, ah, man, this doesn't quite work because sine's not always less than 1. And here's where you have to realize b and theta are not variables. They're constants. We don't know what they are, but they are constants. They are particular values. And so now look at your diagram of the triangle here. Well, if you look at theta, if this is a right angle, which it is, you're actually given that it is to start because they draw the square box here, that's 90 degrees, and there's two other angles. So the most this could possibly be is like 89.99 or something, and then this would be 0.01, but it can't actually be 90 degrees. It can't actually just be 90 degrees because then you wouldn't have a triangle anymore. So theta is less than 90 degrees, strictly less than, and it's also greater than 0. I mean, look, you can't always trust pictures for the precision, like how wide or small it is, acute or obtuse it is, but you can just tell that, okay, that's not 0 because we have a triangle. So it is also strictly greater than 0. Well, if theta is strictly between 0 and 90 degrees, let's take sine of all this. Sine of 0 is still 0, less than sine of theta. And sine of 90 degrees would be 1. But you look at this. This is strictly between 0 and 1. And so the absolute value of sine, theta, is less than 1 in this case. Not all the time. It's not always the case that sine of theta is less than 1. But for this problem, sine of theta is strictly less than 1. And so now this is a geometric series. We're going to put in the first term. So my a sub 1, or my first term, is just whatever we get when I plug in n equals 1. So it's b sine. And the thing I keep multiplying by, if you look at this, this goes b sine and then b sine squared. So that's like I multiplied by sine here. And then sine squared to sine cubed, I multiplied by sine again. And I multiplied by sine again. Or you can just look at what's raised to the n here. Either way, your common ratio, the thing you're multiplying by in this geometric series, is sine. And so, the closed form sum here, the sum of all the diagonals of this triangle, is going to be your first term, b sine, over 1 minus r, 1 minus sine. Again, b and theta are constants, so this is a particular number. The sum of this series is b sine over 1 minus sine, and that is this example of an infinite series within a geometry problem.